Hello student of grade 11. Today we'll learn about the types of relation. There are 6 types of relation: trivial relation, identity relation, reflexive relation, symmetric relation, transitive relation, and equivalence relation. So under the trivial relation we have empty relation and universal relation. Let us learn one by one what is the meaning of each relation. Let's go to empty relation. Empty relation is also called a void relation. Let's go to the definition. A relation R in a set A is empty relation if no element of A is related to an element of A. If there is no relation, we call it empty relation. And mathematically we represent R equal to null phi. This is phi, okay, but meaning is null set or empty set is a subset of A cross A. For example, suppose A is given 1, 2, 3, 4, 5 and the relation is given as A belong to A and B belong to A, and A plus B is 12. Now try to find out a relation where if I add any two number from here is 12. Can you get any number? If I do the maximum two number also, 5 plus 4 is 9. We are not getting 12. So the relation R become, for this the relation R become empty. We cannot find the sum as 12. Or on the same set A, if another relation is given xy belong to A, that means xy can be any number from here such that the product xy is 7. So try to multiply any number here, and are you getting 7 or not? 1 into 5 is also not 7, 2 into 5 is 10. So multiply any number here, you will not get any number whose product is 7. That means in this situation also R is empty. Clear? So this type of relation is called empty relation, where no elements are present. In the relation, no elements are present. Now universal relation is opposite to empty. Here all the elements are present. Okay, a relation R in a set A is universal relation if every element, I'm just underlining this, every element of A is related to every element of A. So here no elements are present, and here every elements are present. For example, they have given A equal to 1, 3, 5, 7. A, B such that this A and B belongs to this number, can be 1, 3, 5, 7, anything. And the condition given here for relation is modulus of A minus B is greater than 0. Now modulus means if you take any number here, suppose I do 1 minus 3, I get minus 2. Modulus means we write always positive. So any number you do here, if I do 1 minus 5 also I'll get 4, because we have to modulus means we have to write every number as positive number. That means every time whatever number you get, if you subtract any number, you will get greater than 0. That means R is universal. Okay, you'll find every time you subtract any number from here, you'll always get greater than 0. So this type of relation is called universal relation. Clear? Another example for universal relation, suppose set A is 2, 5. Now and R is given 2, 2, 2, 5, 5, 2, 5, 5. So just check all the elements are present from the product of A cross A. If I do A cross A also, I'll get this only. So if all the elements are present, that means it's a universal relation. Clear? Let's go to identity relation. If every element of A, set A, is related to itself only. I'm underlining this point, okay? If every element is related to itself, then a relation R is called identity relation. And we represent like this: I equal to A belong to A. For example, suppose set A is given 1, 2, 3, then the identity relation of A is, since it is related to itself, that means it can be 1, 1, 2, 2, 3, 3. It cannot be other than this, okay? Because it must relate to itself only. If there is another element in a set 5, that means it must relate to 5 only. 5, 5. 1 is related to 1, 2 is related to 2, 3 is related to 3. Then this set is called identity relation. If each element is related to itself. Clear? Now, reflexive relation. If every element of set is related to itself, it says related to itself. So you have to understand the difference between identity and reflexive, okay? In this identity, they say itself only. There cannot be any other terms in the set. That means it can be 1, 1, 2, 2, 3, 3 only. It cannot be other numbers. But in reflexive relation, it says related to itself. There can be other set, other order pair also. So, for example, in this is mathematically representation, okay? If AA belong to R, this symbol is for every A belong to A, then R is reflexive, okay? R is reflexive. Let's give the example. If A is 1, 2, 3, and we are given a relation 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3. Now, we can say that as per the definition, if every element of set is related to itself, so from this set, 1 is related to 1, we got 1 point, 2 is related to 2, 3 is related to 3. That means this relation R is reflexive because each element is related to itself. 2 is related to itself, 3 is related to itself in this set. So you can say that R is reflexive. But this R cannot be identity because in identity it says itself only and there cannot be other terms. So in reflexive you can see 1, 1, 2, 2, 3, 3. They are related to itself, but there are another order pair also. Clear? So if there are another order pair also, we can say R is reflexive as long as each element is related to itself. But in identity relationship, if we have another terms come like 1, 3, it cannot be an identity relation. It must be related to itself only. There must not be any other order pair. So in reflexive, they are related to itself and other order pair also may be present. Okay. So note this point. Okay. Every identity relation is reflexive. This relation I can call reflexive, but this relation I cannot say identity. Clear? So every identity relation is reflexive relation, but every reflexive relation may or may not be identity relation. Okay. This reflexive relation will be identity if these are missing, then only this will be identity. Clear? Let's go to the fourth relation. You have to know that in reflexive relation, A must be related to A. Clear? Okay, symmetric relation. A relation R on set A is said to be symmetric. IWF means if and only if, okay? If and only if. This is a mathematical representation. A relation R on set A is said to be symmetric relation if and only if AB belong to R implies BA belong to R. Then only we can say it's symmetric, okay? So mathematically we write like this also. A must relate to B implies B must relate to A. Then only it is symmetric relation. Now in this set, you can see that 5 7, R is 5 7 7 5. So in the relation R, I have 5 7 also, 7 5 also. That means this relation is symmetric. I'm give another example also. Suppose T1 and T2 be a triangle, okay, and the condition given is for the relation, it is given that triangle 1 is similar to triangle 2. So we'll get the relation R. If triangle 1 is similar to triangle 2, obviously triangle 2 will also be similar to triangle 1. That means this relation is symmetric. You have to know that if I can write, if AB is present in R, that means BA must be present in R. Then only we can say it is symmetric. If 5 7 is present in R, then the reverse of this 7 5 must be present in R. Then only we can say it is symmetric relation. Clear? So mathematically we may use this also. Please note down everything, okay? Clear? Transitive relation. Here the situation is like that. If AB belong to R, or A is related to R, and B is also related to if A relates B and B relates C, then AC must also relate to each other, okay? That means in an order pair we can say if AB belong to R and BC belong to R, that means AC must also belong to R. So if this condition is satisfied, then we can say it's a transitive relation. We can say A related to R and B related to A related to B and B related to C implies A must relate to C. Then only we can say it's transitive. I can give an example, like suppose these three lines, the parallel lines are given, okay? If L1 is parallel to L2 and L2 is parallel to L3, that means L1 and L3 also will be parallel. This is a condition of transitive relation. If L1 parallel to L2, L2 parallel to L3, that means L1 is parallel to L3 also. So transitive relation is satisfied. So we can say parallelity of line is a transitive relation, okay? Another example of transitive relation. Set A is given 1, 2, 3, 4. So I'm writing set relation as 1, 1, 2, 3, 3, 4, 2, 4. So is transitive or not? Just check. Why it is transitive? See, 2, 3 belong, I can say 2, 3 belong to R. And after 2, 3, I have to see this 3. 3, 4. 3, 4 also belong to R. And we have to check whether this 2 is in the R or not. 2, 4. Is 2, 4 in the R? Yes. So belong to R. If this condition is satisfied, we can say that it is transitive relation, okay? This cannot be transitive relation. See, 1, 2 belong to R, 2, 3 belong to R, but this 1, 3 is not in the R. So it's not transitive relation, okay? This is transitive because it is satisfying the transitive condition. The last one is equivalence relation. Now, equivalence relation is a relation R on set A is said to be equivalence. Why? When if it is reflexive also, it is symmetric also, it is transitive also. So if it is reflexive relation, if it satisfies reflexive relation, if it satisfies symmetric relation, and if it satisfies this condition transitive relation, then we can say the relation is equivalence, okay? I'm giving one example. Here set A is given as 1, 2, 3, 4, 5, and the relation must be AB such that A plus B is even. If I add A and B, it must be even. So I've made C. If I add 1, 1, it is even. If I add 2, 2, it is even. Or if I add 1, 3, it is even. If I add 1, 5, it is even. Clear? If I add 2, 4, it is even. 2 2 also even. So I find out all the possible relation where a plus b is even. If I add any two number from here, it is even. I've written everything. Okay. Now let us check whether it's reflexive or not. For reflexive, we have to see that the 1 must relate to 1, 2 must relate to 2, 3 must relate to 3, 4 must relate to 4, 5 must relate to 5. So see, 1 1 is there, 2 2 is there, 3 3 is there, 5 5 is there, 4 4 is there. Everything belong to R. That means R is reflexive. Clear? Now let us see the condition of symmetrics. For symmetric, what we see, if 1 3 is there, 3 1 also must be there in R. So 1 3 and 3 1 is also there in R. See, 1 3 is there, and the opposite 3 1 is also present in R. That means it is symmetric. So each element must be like that. So 1 5 5 1 is there, 2 4 4 2 is there in this set, 3 5 5 3 is there in this set. That means we can say R is symmetric. If the order pair is reversed also, if it is present here, that means it is symmetric. Okay. For transitive, what is the condition? If you get confused how to make this, don't get confused. Okay, simple. I have to use this number, and the condition given here is a plus b is even. So I use 1 plus 1 is even. We get 2. 1 3 is even. 4 1 5 is even. 2 2 is even. 2 4 is even. 3 1 is even. So I wrote all the relation. Okay, all the order pair in this R. Now for transitive, what we have to see is 1 3. We have to use 3 numbers. See, 1 3 belong to R. So next we have to see 3 something. Don't use 3 1 because same number only. I'll use 3 5. See, 3 5 belong to R. So we have to check whether this 1 5 is in the R or not. 1 5 also is in R. That means we can say transitive, but it must satisfy each element. Okay, 1 5 belong to R. We can say 1 5 is in R. And connected to 5, we have to see 5 3 belong to R. 5 3 belong to R. Now we'll see whether 1 3 is in R or not. So 1 3 is also in R. Likewise, I wrote everything. Okay, so every element is connected. 3 1 belong to R, 1 5 belong to R, and 3 5 belong to R. 3 5 is in R, and 5 1 is also in R, and this 3 and 1 also belong to R. That means R is transitive. So if it is satisfying reflexive, symmetric, and transitive, we can say that this relation R is equivalence relation. Okay, thank you. You can pause the video to write everything. Thank you so much.